Hello everyone, my name is Jijing Chen. You can call me Annie. Today I'm going to present my master project on collision predictions and avoidance system for UAVs. In this presentation, I will go over our project's overview, hardware and software we use in the project, and some simulation and flight tests. Our introduction to our project as an unmanned aerial vehicle, which is UAVs, is more and more in nowadays. There is a demand for safety operations in high traffic area. So for fully autonomous vehicles to be used in the dynamic environments, a collision avoidance system must be significantly robust as to ensure that the probability of collision is equivalent or less than the manned aircraft. So we will look at our project's overview. The objective of our project is to use automatic dependent surveillance broadcast, which is ADS-B transponder, to determine the autonomous collision detection and avoidance between two UAVs. So it will broadcast and receive ADS-B data in real time. To perform an onboard processing of collision avoidance algorithms, and also demonstrate feasibility of using ADS-B transponder for collision avoidance between small outdoors UAVs and large aircraft. Some potential application can be used as during January 2020, FAA had required that all the aircraft operating in Class A, B, C, and certain Class E airspace must be equipped with ADS-B out. And using ADS-B for UAV collision detection will help UAVs avoid collision with not only similar equipped with other UAVs, but also with manned aircraft. And then it can help in integrate of UAVs into those airspace for widespread application, and use UAVs and help UAVs have met equivalent level of safety. So here is a video to show you what is ADS-B.
ADS-B and NextGen are revolutionizing aviation. Skies around the world are becoming increasingly crowded. In the U.S., the Federal Aviation Administration ADS-B and NextGen are revolutionizing aviation. Skies around the world are becoming increasingly crowded. In the U.S., the Federal Aviation Administration estimates that rising numbers of flights and passengers will overwhelm the current air traffic control system by 2015, leading to an increase in delays, higher costs, and greater environmental impact. To meet this challenge, the FAA is building NextGen, America's air traffic control system of the future, which will make air travel safer, more efficient, and better for the environment. The backbone of the system is a new technology called Automatic Dependent Surveillance Broadcast, or ADS-B. ADS-B enables the widespread use of satellite-based GPS technology in aviation. It provides air traffic controllers and pilots with information that will help aircraft efficiently navigate our increasingly congested airspace. So how does it work? ADS-B allows planes to determine their exact location using GPS. That information is broadcast to other nearby aircraft and ADS-B ground stations, which relay the information to air traffic controllers. Additionally, a signal with flight, weather, and radar data is broadcast back to the plane. To make this possible, aircraft will be required to have equipment that continually broadcasts their position, and optionally, additional equipment that enables the aircraft to receive those messages from other planes, as well as information from ground stations. This continuous and nearly instantaneous cycle of broadcasts gives air traffic controllers and pilots a complete and more up-to-date picture of their airspace. ADS-B provides updates 12 times more frequently than radar, which means better coordinated takeoffs and landings, less time sitting on the ground or circling in the air, more direct routes that shorten flight times, and fewer delays. Increased airspace efficiency is another chief benefit of ADS-B. The technology puts more information in the hands of pilots, who will now have access to air traffic control data on display screens right in the cockpit, while controllers will guide them from displays which will be more accurate than ever before. This extra layer of data enables advanced air traffic control procedures, allowing aircraft to fly more closely together with fewer instructions from the ground. ADS-B also benefits the environment by enabling a more direct approach and a power-saving continuous descent to the runway. For example, an airliner using these procedures during every landing would save enough fuel to reduce its annual carbon emissions by an amount equal to that of more than 100 cars. ADS-B will have direct effects on local markets. For example, in the Gulf of Mexico, ADS-B stations installed on offshore oil rigs are providing full air traffic control coverage over the Gulf for the first time in history. ADS-B dramatically increases efficiency for both low-altitude helicopter traffic servicing oil rigs and for high-altitude air transport aircraft traversing the Gulf. Right now, ITT is working with the FAA on a nationwide rollout of ADS-B. ADS-B technology will enable air travel that is safer, more efficient, and better for the environment. This technology, a cornerstone of NextGen, will revolutionize the future of flying. And it's on its way right now.
Okay, so now we know what's the ADS-B, we will look at the hardware of our project. So first is our test vehicle. Our primary test vehicle is a fixed wing airplane. You can look like it's a picture like this. And then the model is a E-fixed carbon Z cube. And it's a large scale RC plane capable of carrying payload. And electric models for quick turnaround allows many flight testings. It's easy to integrate onboard computer, flight controller, and others hardware. And then it's also equipped with ADS-B and all the hardware that I was talking about. And it's using as our ownership during the flight test. The secondary test vehicle is a quadcopter. The model is a lightweight F450 frame, and it is brushless motors for higher efficiency. And we minimize the wire, decrease the weight for increased flight time. And it also equipped with ADS-B transporter, GPS, and the pit stop. And it's used as an intruder during our tests. So here is the layout for our hardware. So the first one you see on the left hand side is a ADS-B receiver. It's an ADS-B transponder. It's a pin 220 in and out, so it can detect range of 100 miles and then 1 second update interval. And then the second one is the GPS that come with the ADS-B. And then besides that, we have our own GPS model to enhance the precision of our location. And then number 4 is our pit stop cube. It is our flight controller, and then it also had the function of flight test and autopilot of flight safety. And then number 5 is telemetry that we can use to communicate with our ground control station. And then it had a range of 25 kilometers. And 6 is our onboard Intel computer stick, which is how our avoidance algorithm. As you see in the title, it's called previous setting. It's because starting from this year, FAA had a new regulations of using ADS-B out on UAVs. Because ADS-B out is broadcast to all the other vehicle and also to the ground control station, it will overwhelming the traffic and then also the infrastructure. Because of that, so FAA had limit ADS-B out can use in the civilian UAVs. So because of that, we had to make some change our projects. We had to use a customized ADS-B substitute solution to solve that problem. At the end, we decided to use SB radius models, which can be also broadcasting all those data we need to our intruder, and then we can also receive our information from our intruder to perform our collision avoidance algorithm. So here is the current hardware setting. So mainly the big change is for the data transmit, we're using SB, which is a detection range of 300 meters, which is smaller, which is less than what we use as ADS-B, but it can serve our purpose. And then also 1 second update interval. And 2 is our Intel computer stick as before. and we also still have our PSOT. And then since we don't have the ADS-B with the GPS, then we will use our own GPS model to get our GPS location. And then we also use a little bit different telemetry to communicate with the ground control station, which had a range of 300 meters as well. And then here is a setting of our flight test communication. In here, left-hand side is our own shift, as you see before. And the right-hand side is the intruder hardware. We use the Raspberry Pi as the computer to contact with the PSOT, and then computer also had the SB, then to communicate with each other. So between the SB, they will transmit their flight test in flight data, for example, latitude, longitude, airspeed, velocity, and all the data that we need to calculate our collision prediction and avoidance. And then in here, we had a telemetry to communicate with the ground control station. So we can monitor our own fixed wing, make sure that there's not any issue on it. And here is a setting of the simulation communication. So because we want to test our algorithm before we do an actual flight test, which will involve another vehicle, we will use a simulation for a mission planner. Later, you will know what is the mission planner mean when we go to the software. And then the mission planner will simulate a fixed wing vehicle, and then like it will do some mission in the mission planner, and then it might intrude with our own shape aircraft. Then they will also transmit like virtual vehicle flight data. And here we will see our you will see our software. So the first software we're using is Autopilot. It had the autopilot system supporting many vehicles as like multi-copter, traditional helicopter, fixed-wing aircraft, boat, submarine, and rollover, and more. So there are 4 main functions that we are using of Autopilot in our project. So first is the unmanned vehicle. We will use Autopilot to control our fixed wing and also our copter. And the hardware it was using is the PSOT that you see before. It used as a vehicle controller. And the firmware is the brain of the controller that you embed it into the PSOT. And then next is the mission planner that we use as our ground consultation and also simulation. So here is an example of the firmware. So in here there are many different types of vehicle that you can pick. So you pick one of the vehicle that you want, and then you embed it, install into the PSOT. Then the PSOT can perform that kind of vehicle behavior, because from the plane or a copter or a helicopter, they all behave very differently. For a quadcopter, you can do like immediate takeoff and then do a sharp left turn and right turn, which is a plane cannot do. So it's very important that you embedded the correct framework to your PSOT to do the correct behavior that you want. And then here is a mission planner. So here is a map on the mission planner. If you're using an ADS-B, that you can show on the mission planner, you can see the other aircraft. So here is the real airplane that in the air at that time we received the ADS-B. And then that is a picture from last year, because last year we still allowed to using ADS-B, but unfortunately this year we are not allowed to using ADS-B anymore. And here is the mission planner monitoring the mission. So here is just an example. The aircraft will taking off and then try to follow the path to fly to each waypoint. So for example, here's the home, and it will go to waypoint 2, 3, 4, and etc. So in here we can monitor our our aircraft, like looking at the altitude, ground speed, vehicle speed, and latitude, longitude, etc. Beside monitoring, we can also like set mission from the mission planner and then load it to the PISA to ask our airplane to do that mission. So in here is you can click on the screen to set several waypoints, and then it will form a path. Then you can write the waypoint to the PISA, and then the PISA will have those missions. So the next system we use is Maolink library. So Maolink is a message protocol that we use to communicate between drones. So it is using a hybrid publish and subscript, and also point-to-point decide pattern. So as here is an example you see here. Here is the drone that it communicates to the ground control station using Maolink library, and and then something is transmit everything about the drone. It will send it to the mission planner as you see before, and also it will send to our onboard computer as well. So for example, the heartbeat of the drone, and also like altitude, attitude, and also like command that we send to the drone, and also acknowledgement. So finally, the system we're using is called Drone-Key, which is we use to develop our own application to control our drone. Here is an overall function you see within the hardware. So here is a mission planner which using mail proxy communication, is using wireless communication with the Maolink. And then here is our onboard computer. On the intruder, we're using Raspberry Pi. On our fixed wing, we are using an Intel computer stick, which is had the Drone-Key installed, and then it will wirelessly connect to the PISA, and then it will communicate to the Maolink. Then Maolink will communicate to the audio pilot. Then the audio pilot will control the PISA will control the drone. So on the picture here, I had another telemetry, which is a controller for our pilot in case anything happen during the autopilot. So our pilot can take over the control. So in here you see that the Drone-Key is communicate with the autopilot using the lower latency link, and the API communication with vehicle is using Maolink library. And then here is the overall operation of our project. So first is we had two types. One is using in simulation, which called sim. Another one is using actual on a flight test, which called CA, stand for collision avoidance. And then first is in our main function, we will create a plane object, and then we will check if the project is armable. If it's not armable, then we will. If it's armed, if it's not armed, then we will arm and take off the plane. So when it's take off and then start to perform its mission, then we will have a plane run, and then it will go to create 4 threads. One thread is to save to file, which is save all the vehicle data to the file. And the next one is send vehicles data. So it's sending the data to the data out is like the customer ADSB, but we are using SB to broadcast it. And in here, if we are using simulation, then it can just call this function and broadcast to another SB. But if we are using flight test, then it had to involve with another function, because in flight test is a little bit different. So similarly, we will receive other vehicle data as well using SB. And at the same time, we will predict collision when we receiving all those data. So when we predicting collision. So if collision predict, then it will calculate an avoidance return and try to fly to an avoidance waypoint. And after it perform the avoidance, it will try to back to its original path. So here's the some code that we were using. Here is example of the library that we were using. As you see, here's a junkie and here's the modeling library. And we create a prank class to hold it. And then, as I say, for the sim and the for the actual flight test CA, there are difference. And here is a little bit detail of the main function. So first is try to create a connection. So if we are using a simulation, then it will connect to using TCP to connect to the mission planner to use the simulation. And if we are using actual hardware, then we will connect to using this hardware and establish a connection with the pizza. So we had the connection string we passing into the plan object, and then it will start to create a plan object. So now we had the plan object, we will try to perform our mission. So it will first try to arm and take off. And then after it's arm and take off, and here is try to do the avoidance when it's doing some partition inside. So here is a little bit more detail when we go into the plan class sim. So first we need to establish the SB communication so we can communicate with other aircraft. So this is the port that you that you put into your device. And then as long as your other aircraft, they are in the same range, then like they can communicate. If it's a different range, then they cannot communicate. And then here is the initialization of the plan class. So first it will see that if the plan created or not. If it's not, then it will create a plan that which is using junkie library to create a plan. And then that's how we can communicate to the junkie. Then we can communicate to the audio pilot. And then here is all the initialized variable that we need to use later. And then when we had all those variable, then how do we get those variable from our hardware, which is from our pixel, is setting the listener. So we listen from the modeling library that we get from the pixel to and then we know the all the latitude longitude about our own vehicle, and the SB is getting from the intruder vehicle's information. And here is some function that we will using in our flight test. Also simulation. So for example, if it's armed, if it's not armed, then we will arm and take off. So before it's arm and take off, it will download mission, and then like during mission it will add takeoff. And then for the download mission is what you see before in the mission planner, that we set out several waypoints, and then it will download those waypoints into our pixel, and then from pixel we will download into our code here. Then we know what is our mission. Then we can modify the mission and then modify our collision avoidance. And then here is to show you the fourth thread that we were using. In here is only three thread, which is can perform very well. And then later I will show you another thread is for our partition, which is still under develop. So in here is to save to file that we will save the information about ourselves, which is our ownership vehicle. For our fixed wing, we will store like latitude, longitude, altitude, velocity, airspeed that we will need to use to calculate our collision partition and also avoidance. And then similarly, we will send this to the intruder, and we also receive the similar data from the intruder. And here is our collision prediction avoidance sequential operations. So as you see here is our hardware percent in the blue. So our pixel or autopilot that will communicate with, we will get the GPS data, and also we will send to the mission planner using telemetry. And then we get all those information we will get from our computer stick. And then our computer stick can send those data using SB to broadcast. And then while doing that, in the computer stick, we will request a mission waypoint, and then it will in the loop. Then after the mission is received, then it will perform mission. While performing the mission, it will see if the collision is predict. If the collision is predict, then it will calculate the avoidance waypoint, and it will navigate to an avoidance waypoint. And it will try to generate a avoidance waypoint and navigate to the avoidance waypoint, and then after is back to our original mission path. In here is to show our collision prediction. So our collision prediction is extrapolated in the intuitor and our own ship position that we are using the linear extrapolations. And then we are using a fixed fixed timestamp, which is 0.5 seconds to determine the prediction resolution. And then we will predict 10 future points. So in here, that we will break us our own shape and intuitor velocity into 3 components. Then it will extrapolate the position in the fixed time interval. Then if the position is closer than the limit defined by the tolerant variable, then we will say the collision is detected. So in here, we say the collision will be detected in this area. So here's some code about our collision prediction. And in here, we had the range of 10, which is we predict 10 future points. And then here is for each variable s, y, z, we will want to get their future distance. And then we go to the function, and then here is getting the future position. It's just simply the linear extrapolation. So position times 1,000, because what we get from the modeling library is in kilometer, and we will need to time to 1,000 to get meter, and then velocity times the time. And then here is the collision predict. So if we say the distance between the two aircraft, so you see that we say position S and V2, which is intuitor position S. If the distance between them is less than a tolerance that we said before, then we say there is a collision. If not, then we say it's false. So you see the collision predict is in here. So it will predict in 10 future points as well. If it's true, then it will print out it is collision predict. Then later it will it will set a thread, and then it will go to the avoidance waypoint. And here is our collision avoidance algorithm. So we use ellipsoid-based geometric avoidance. So here is our intuitor vehicles that we perform ellipsoid space, that the length of the ellipsoid is based on its velocity. And then here we call this a safety bubble. So the idea is to avoid getting to the safety bubble, we want to go to the tangent planes of the surface. So how do we determine which point we're gonna go to? Then first we're using the energy function to determine the z altitude. And then we will use these 2 complicated functions that I will not explain in more detail. But these 2 functions is calculate 2 tangent plane of the surface that you see on this ellipsoid. So as we will get two tension point, which is S, and another one is Y. So in here we got S and Y. That we got these two waypoint that we want to avoidance waypoint that we want to fly to, and then we will choose to use the shortest path that so from our waypoint, so which we will choose waypoint 1 in here. So the example is like this. Suppose it should be waypoint 1 in here, but to make it more clear and easier to draw, we draw it like this way. But as you see, and then our imagine our aircraft is flying toward to the plane, and because it's hard to draw it, so we draw like this way. But imagine that it's flying toward to the intruder, and then it will calculate the waypoint that we using those function, and then here is the tangent plane, and then it will fly to over here. And then here is our avoidance waypoints algorithm that we were just using this function, pretty much using this equation to perform our avoidance waypoint, and pretty much just those equations. But right now we are facing some difficulty is based on the calculation, we're supposed to get a GPS valuable. But in fact, that we were getting some valuable that imaginary value. So we are right now we try to fix that problem to see if there's something wrong in our calculation, or try to figure that out. So now we will look at our simulations. So the first simulation I will show you is a single simulated fixed wing that we want to test our collision avoidance algorithm by itself. So we are using the mission planner simulation. So in here, it take off and then it's try to perform its mission. So you see it's flying to the waypoint, and then when at waypoint 2, and then I was saying that, oh, imagine there is an intruder coming, fly to the waypoint, avoidance waypoint. So you see it do fly to avoidance waypoint, and then after it fly to the avoidance waypoint, and then it coming back to its original path. So here is so that's why we're using a simulation to test if our collision avoidance is successful or not. And the next simulation we're using is using two simulated fixed wing UAV. So two reasons we want to test. One is to test our SB communication. And then the second one is to test our collision avoidance algorithm with an intruder. So, but right now, current setting, you see that we need to have two computer connect with the two SB. This is the SB, and then they will exchange their flight test data, as you see in here. So here is vehicle A, and then receiving vehicles B flight test data. And then here's vehicles B receiving vehicle A flight test data, and then they are flying toward each other. And right now, at this one, we did not include the did not include the collision algorithm testing yet, because we are mainly testing the SB communication. And here is our flight test, our actual flight test videos. So you see that this is our own shift. Our fixed wing aircraft is, I think is at that time is doing the autonomous flying, is doing autopilot, and then we have our own ship just sitting on the ground at that time, and then like at that time it detected there is an intruder, and then it was doing loitering, because our we build our algorithm step by step. So first it said that, oh, if you detect detect an intruder, you loiter at certain point. And then next step we want to do is fly to that point, and then next step is fly back to its original path. And then here is a graph of our flight test results. So in here is it take off over here, and then here is a collision or avoidance zone, which is we just put our intruder setting on here. And then if take off, this is the distance for it to take off, and then it try to fly. And then when it's flying, here is some prediction point. And then you see when it's several points where it predicting is gonna get inside the collision avoidance zone. Then it tried to avoid, and then it was fly to this direction. All of it is performed autonomously. And then at that time, we set it to loiter at one of the points. So it's loiter over here. So, and then I had it take off. And then here is a kind of zoom in a certain area that you see that here is at this point here is a predicted path. So which we think is a linear. We want to do a linear prediction, and then like predict 10 future point. And then that is our project overall. If you have any questions, feel free to ask me in Discord. Feel free to ask me in the discussion. I will be happy to answer it.